Alright, so today we're going to be talking about another application of limits, and this one is called relative rates of growth. And in this application, we are going to be worried about comparing two different functions and trying to qualitative or quantitatively argue that one function grows faster than the other or not. And therefore, we uh, restrict our view of functions as they grow towards or as they tend towards infinity. So we're going to be looking at how functions behave as the x value tends towards infinity, and using that knowledge we're going to be trying to qualitative or quantitatively analyze whether some functions grow faster than others. And what I mean by grow faster than others, you might have like already experienced, let's say we have y is equal to e to the x and we have another function y is equal to x. You might have already like seen that if I were to graph out y is equal to x, that would look something like this, whereas y is equal to x squared would look something like, or y is equal to e to the x would look something like this, right? And you can kind of imagine that as we tend towards this positive x direction, as we tend towards infinity, the value of e to the x will always be larger than the value of y is equal to x, and the distance between the corresponding values. So for example, at this random like xi value, the distance between the value of e to the x at that value compared to y equals x is like some distance d. But if as I increase my value of x, this distance between the corresponding points on each curve will continue to increase, right? And when these distances continue to increase, that tells us that e to the x grows much faster than y is equal to x. And we've seen this qualitatively, but how do we kind of formulate ways and methods to determine which functions grow faster than others or which functions grow at the same rate? And if functions grow at the same rate as the others, this distance between the two functions does not really change too much. And so let's just get into how we'd formally determine the comparative growth of between different functions. And there's a lot of applications of this in like computer science, so it's probably something you might see later on. So, definition. And to find out whether functions or the relative rates at which functions grow, we'll be utilizing limits. So, let f of x and g of x be positive for large x, and we're going to be comparing the growth as x tends to infinity. So f grows faster than g, and then you can also say that g grows slower than f as x tends to infinity if limit as x tends to infinity of f of x divided by g of x is equal to infinity, or limit as x tends to infinity of g of x over f of x equals 0. And this kind of makes sense, right? If f is growing at a much faster rate than g, then as we tend towards infinity, the quotient of this will continue to get larger and larger because the rate at which f is growing does not match the rate at which g is growing, and so our numerator will be growing much faster than our denominator, and hence the quotient will continue to increase. And so finding out these limits tells us the relative rates of growth between f and g. And likewise, if we were to just take the reciprocal of the this fraction, we would get g over f of x. And you can kind of think of it as being 1 over infinity as we tend towards x equals infinity, and therefore if we get 0, then you can say that g grows slower than f, or f grows faster than g. So both are equivalent definitions. And the second part says f and g grow at the same rate as x tends towards infinity if the limit as x tends to infinity of f of x divided by g of x is equal to some constant L, which is not equal to 0. Because if it was equal to 0, that means g would be growing much faster than f, right? But if we have it, if the limit is equal to some constant, then that says that the as like in the limit as we go towards infinity, the quotient will become a constant, and so one function is not growing at a much faster rate than the other function. And an important implication of this, which might not be fully intuitive, is that this definition implies that if we have an equation of y is equal to 2x, and if we have y is equal to x, if we were to take the limit as x tends to infinity of 2x divided by x, we would get 2, right? And that implies that 2x and x grow at the same rate. And we know that even though as x tends towards positive infinity, the values that the y equals 2x takes on is always greater than the values that y equals x takes on for the same x's. The way that we have defined the rate of growth still means that even though 2x will be like the equations, like this might be y is equal to x, and then we have y is equal to 2x right here. Even though one graph is completely like greater than the others, they grow at the same rate because of the way that we have defined how functions grow and how we're comparing the rates of growth. And so that implies that if we have functions in like the same kind of class of functions, both of these being linear, they have the same growth rate. And this is like something important to notice, that rate of growth is not necessarily related to a function being greater than or equal to another function. So these are two sort of separate things, even though like there might be some relation between them. And so let's work on some examples. So example 1, let's compare the growth of e to the x and x squared. So I'm going to take the limit as x tends to infinity of e to the x divided by x squared. And right now, I would get infinity over infinity if I were to plug in infinity as the value of x. So this is indeterminate, but I can use L'Hopital's, and I can rewrite this as being equal to the limit as x tends to infinity of e to the x divided by 2x. Again, that would lead to an indeterminate form of infinity over infinity. So let me reuse L'Hopital's, and I get e to the x over 2, and now I'm just left with infinity over 2. So that's equal to infinity. And therefore, e to the x grows faster than x squared. And this is coming from our definitions of how we sort of related the limit behavior as x tends to infinity with how functions grow relative to each other. Let's work on a second example. Show ln x grows slower than x and x squared. So limit as x tends to infinity of ln x divided by x, we would, in order to show that this function grows slower than both x and x squared, we would expect this the limit to become 0. And so right now we have infinity over infinity, which is indeterminate, but L'Hopital's can help us. And so taking the derivative of the numerator, I get 1 over x, and then the denominator's derivative is simply 1. And now I get 1 divided by x, and as x tends to infinity, that becomes 0. And so ln x clearly grows slower than x, and you can do something similar with the x squared example. As we take multiple derivatives, the first one would give us 1 over x divided by 2x, and that will give us 1 over 2x squared. And the limit as x tends to infinity of that will simply equal 0 as well. And therefore, ln x grows slower than x and 2x. The third example is compare rate of growth of log base a of x and log base b of x. So let's apply the definitions. Limit as x tends to infinity of log base a of x divided by log base b of x. Naturally, to compare these, we want them to be in the same base. So let's use the change of base formula to rewrite this as ln of x divided by ln of a divided by ln of x divided, this should be a, divided by ln of b. Now, simplifying this fraction, I get limit as x tends to infinity of ln b times ln x divided by ln a times ln x. And these two terms are the same, so they cancel out. And I end up with ln b over ln a, and that's just the division of two. That's just dividing two constants, and you can just rewrite this as log of b base a. And this is a constant, and therefore these two logs grow at the same rate because we got back a constant that's not equal to 0. So grow at same rate. All right, so we've seen a good amount of examples of us comparing rates of growth. And there's an important property that can help us easily simplify certain problems. And this is the transitivity property. Of growing rates. And it just says that if f grows at the same rate as another function g as x tends to infinity, and g grows at the same rate as h, as like h being another function as x tends to infinity, then f and h also grow at the same rate. So if you have seen different transitive properties before, this is the same idea, but just for relative rates of growth. So given that a function f grows at the same rate as g, and now we're given that g grows at the same rate as this other function f, or this other function h, therefore f and h must also grow at the same rate. And that's because of this like middle value g that relates f and relates to h. And so let's see an example of using this transitive property. So let's say that we want to show that the function f of x is equal to the square root of x squared plus 5 grows at the same rate as g of x is equal to the square, or 2 times the square root of x minus 1 squared. So we can kind of see that like the relative growth rate of this function in the limit will be around the function y is equal to x. And that's because the leading term over here has an x squared, and then when you square root that, our leading term will have the same as like x to the power of 1. And so the family of functions that it grows around will be y is equal to x. And then using a similar argument here, we're going to see that, you have x to the 1/2 is the leading term inside of this square term, and we're just simply squaring that. So our leading term will, when we simplify everything, has the degree 1, so y is equal to x. So that can be our common function that we relate these two functions to. So let's show that f of x and y is equal to x grow at the same rate. So limit as x tends to infinity of the square root of x squared plus 5 divided by x. In fact, we can actually simplify this without using any special rules. So that's the same thing as limit as x tends to infinity of the square root of 1 plus 5 divided by x squared. I just took this x and divided it inside the square root. And we know that 5 divided by infinity will be 0 over here. And so this limit simply simplifies to the square root of 1, which is equal to 1. Now, let's compare the growth of g of x and y is equal to x. So limit as x tends to infinity of 2 square root of x minus 1 divided by x, and this is squared. Now, I think the best way to go about this this function is, again, me taking the square, so doing this where I have limit as x tends to infinity of 2 root x minus 1 squared divided by the square root of x squared. And now I can just do the division in line. So that's becoming limit as x tends to infinity of 2 minus 1 over root x squared. And now over here, 1 divided by the square root of infinity will tend towards 0. And so we're simply left with 2 minus 0 squared. And so our limit evaluates to 4. And therefore g of x, and so we've proved that g of x grows at the same rate as y is equal to x, and y equals x grows at same rate as f of x. And therefore, by the transitive property, g of x and h of x, or sorry, not h of x, f of x grow at same rate. So sometimes evaluating the limit of f of x divided by g of x might be more complicated than us choosing a middle function and then using the transitive property. So sometimes the transitive property can come into use. So one thing you guys might have noticed is like us using this terminology like grows and then insert like faster, same rate, slower is kind of annoying, right? So there's actually a notation that simplifies all of this and kind of describes to us the relative rates of growth between two functions. So let's go over that notation, and this is called the O notation, where this O kind of stands for like the order of growth. And so I'm going to introduce two things, one thing called little o and one thing called big O. So if we want to show that f is of smaller order than g, and that just means f grows slower than g, strictly slower, that is, also. F is a smaller order than g, which means that if f is of smaller order than g, then the limit as x tends to infinity of f of x divided by g of x will become 0. Because we're saying that f grows slower than g, and that's the same thing as saying f is of smaller order than g, and because of what we have seen before, it must imply this limit relationship must hold true. And when this limit relationship holds true, we can write this, f is equal to, and this is the character O, so like the letter O, f is equal to O of g, and that's just saying f is little o of g. And this notation is a shorthand which is used very often to just say that f grows slower than g, or equivalently saying f is of small order than g. So you use that little o notation to represent whenever one function grows slower than the other function. Now, there's another O notation that's also particularly of particular importance, and that is when we want to represent f is of at most the order of g. And so here, when we want to show that f is of at most the order of g, the limit as x tends to infinity of f of x divided by g of x must be less than or equal to some constant m. And in this case, m can be equal to 0. What this is saying is that if f is of at most order of f is of at most the order of g, that all that means is the highest rate at which f grows is the same rate as which g grows, but f could also be growing at a smaller rate than g. And if it is growing at a smaller rate than g, then this limit will evaluate to 0. So when f is of at most the order of g, f can be equal to little o of g, but it could also be equal to, or it could also be growing at the same rate as g. So you're like, it's not as strict of a comparison as this previous notation of f being little of g, because that implies that f has to grow at a strictly lesser rate than g. But in this other case, where f is of at most the order of g, we write it as f is equal to, and now this is a capital O of g, and this is set as f is big O of g. And this implies that f could be growing at a slower pace than g, in which case this limit evaluates to 0. But f could also be growing at the same rate as g, in which the limit will evaluate to a non-zero constant. And so the big O notation just implies that it's like more like a traditional less than or equal to relationship if you want to think about like functions growth as your inequalities, whereas this little o notation is a strict inequality where it's more of a less than relationship. So that's the main difference between the big O notation and the little o notation. And so let's do one example related to that. So show that x plus sine x is big O of x. So what we want to do is we want to evaluate the limit as x tends to infinity of x plus sine x divided by x, and we expect it to be some constant. So that's the same thing as limit as x tends to infinity of 1 plus sine x over x. This is just going to be 1, and then we know that this is the same thing as limit as x tends to infinity of cosine x divided by 1, and then the plus 1 because of this. And that's just or actually, sorry, we don't actually even need to use L'Hopital's rule. Sine x is always bounded between -1 and 1, and then this is going to tend towards infinity. So this is actually not a indeterminate form. This is clearly saying that this limit will become 0, so our total limit is equal to 1. Therefore, because the limit evaluates to a constant 1, x is big O of n. So you can write x plus sine x is equal to big O of x. Alright, so we showed that. Now let's just do another example. So this is example A. Example B. Show that e to the x plus x squared is equal to big O of e to the x. And so if you were to find the limit as x tends to infinity of e to the x plus x squared divided by e to the x, this would simply be equal to the limit as x tends towards infinity of 1 plus x squared divided by e to the x. And in a previous problem, we showed how x squared grows slower than e to the x. So this limit will simply tend to, in the limit, this will simply tend towards 0. So we also get 1 in this case. And because we valued it to a constant, this statement is true. Notice that let's say we were evaluating the limit as x tends towards infinity of e to the x divided by x, that would be infinity, right? Because this is not a constant, we cannot make any claims about big O. Well, we cannot say that like e to the x is equal to big O of x. This is not true. So this is not allowed. So make sure that if you get infinity, then you cannot like say that the function on the numerator is equal to big O of the function of the denominator. That's a common mistake. But yeah, that was relative rates of growth. Basically, another application of limits, and it helps us kind of quantify um, how different functions are growing and what pace they're growing at, and it's very important in applications of computer science as well as mathematics.